thank you very much to the NSTF for inviting me here. I suspect my presentation would have been better at the first symposium, but I'm afraid you're going to have to listen to it today. I am Principal Scientist at CIMERA, one of the DST NRF Centres of Excellence, and I'm also Prof of Economic Geology at the University of Witwatersrand. And I'm going to talk about critical raw materials, hype cycles, and the fourth industrial revolution. I've actually just come back from Edinburgh and the third international conference on critical raw materials, so I'm actually passing on information and discussion that was talked about there. There's a serious answer to what critical metals are, those whose availability is essential for high technology, green and defense applications, but vulnerable to politically or economically driven fluctuations in supply. The text in red would probably not have been in any definition of about 10 years ago or earlier, and the definition you have, the materials that you consider to be critical, are totally dependent on where you are, which country you're in, what industries you're considering are important, and your perceived risk of future supply and your perceived demand. That is not actual reality. All of those are subject to change. I've also put what I call a cynical definition, any metal or material that can be so declared to enhance the spin by any junior exploration company, any mining company, any academic in research, or any NGO, or any governmental organization to obtain funding money or public awareness of a particular critical metal. Since 2010, not just academics, not just the people who are sort of working on them, have become aware of critical raw materials. There was the first book, Critical Metals Handbook, came out in 2013, with essentially authors from the British Geological Survey and the United States Geological Survey. But there's nothing new whatsoever in this concept. It's highly likely that the Romans invaded the UK for tin back in sort of pre-Christian days. In World War II, tungsten was a vital commodity for munitions in the Second World War, and Panasqueria in Portugal managed to supply both sides in the conflict. In 1983, the US published a paper on strategic and critical non-fuel minerals, problems and policy alternatives, a response largely to the oil crisis of the 1970s. Those of us that are of that age can possibly remember queuing at petrol pumps. I can remember my father having to queue for at least half a day to fill up his tank of petrol. So critical raw materials is not a new concept. But this is probably a diagram from the report that started it all off recently in 2010. It's an EU report which identified 14 critical metals: rare earth elements, PGM, niobium, germanium, magnesium, gallium, antimony, indium, tungsten, fluorine, beryllium, cobalt, tantalum, and graphite, out of 41 which were defined as critical based on economic importance along the x-axis and supply risk along the y-axis. And we can see that rare earth elements are right at the top. PGMs, with South Africa the main producer, are particularly critical. Cobalt, graphite, and lithium are there. In my talk, I've highlighted in particular lithium, cobalt, and graphite as components for lithium-ion batteries, which at the moment are particularly important in the electronic vehicle industry. I've also highlighted rare earth elements in terms of sort of magnets in the electronic vehicle and wind farm industry as well. In 2011, a consultancy company for the German government came out with their own version of this, and they decided that rare earth elements, palladium there, but antimony, rhenium, and germanium were identified as the main elements from a German perspective, particularly, probably, for their car industry. So the elements that you think are critical depend on where you are. Countries are now producing risk lists. There's a 2011 one there, there's a 2012 one there. Of interest, in 2011, the British Geological Survey reckoned that PGEs had a very high risk. By the time 2012 came along, it wasn't as risky at all. One thing to note that in 2012, the main producer of many of the critical raw materials was in fact China. This obviously has geopolitical implications, particularly for Europe, America, and Japan. There's the 2012 risk list again, and a 2015 version. PGE is still relatively less risky, if you like. Rare earth elements still at the top. China, with its mine in Bay and Obo and its iron absorption clay deposits, is the principal producer of rare earth elements in the world. 2013, another version comes out, again from the EU, and 20 critical materials were identified out of 54. It's interesting here that there's no dimensions and no scale along the X or Y axis. There is an incredible amount of debate about how you actually calculate criticality, both in terms of geopolitical risk and in terms of supply risk. There is no agreed way at all to decide how to actually sort of calculate those metrics. There's an interesting, slightly provocative statement at the bottom. The world contains the energy and mineral resources needed to sustain 10.5 billion. The level of the world population is expected to reach in 2100 at a European standard of living for hundreds of centuries. That is probably contrary to a lot of things that get written or listened to or seen. But it does mean that there is no consensus, really, about how long our natural resources will last. In all fairness, Catalyst does actually point out that most of those resources are in fact in seawater in the long term. So potentially extraction of metals and materials from seawater is something that we should think about. 2017, another new list, even more commodities, 9 more than 2014. Obviously, everything soon will be critical. Interesting that even though this came out in 2017, lithium had still not made it onto the critical list, in spite of the increased expected demand for lithium-ion batteries in electronic vehicles. This is something that was developed by a person called Fenn, working for the Gartner Group in America, to describe the performance of emerging technologies. It's somewhat Zen-like in its terminology. Along the bottom we have time, along the y-axis we have expectation oblique price. And this is the sort of R&D phase, and we then have an innovation trigger, and everything takes off, and we think it's going to be the best thing since sliced bread, and we have a peak of inflated expectation. We always think that a new technology is going to be absolutely wonderful, it's going to change our lives dramatically, and life will be so much better. We then fall off the edge of the cliff along into the trough of disillusionment down at the bottom. But ultimately, things get a bit better, because essentially we realize that yes, it's a good thing, perhaps not as good as we thought it was, but ultimately it will continue to grow, and we end up with the plateau of productivity. And in fact, you will see that the plateau of productivity from the sort of R&D stage is actually a little bit higher in terms of sort of expectation, price, demand, usage, etc. It's not really a cycle. It's been criticized for that, and it's really a sort of a bit of a feedback loop. And one thing it doesn't really illustrate is what actually happens if the technology fails, because essentially the graph will just come down here. What happens if the plateau of if the peak of expectation is a false summit, essentially? Potentially we could go off in this direction as well. So I think from this point there are a myriad of paths. This only shows one. Timescales will vary. I appreciate that you probably can't read too much that's on here. There is big data. This is a 2014 version of the hype cycle with various technologies at some point along it. In this case, it's being used for emerging technologies. We have big data there. We have 3D scanners here. And there are various things that I've never really heard of on the left-hand side, including quantum computing. There may be people in this audience who are much more aware of that than I am, but will it actually make it to the plateau of productivity? It's also possible to apply this to commodities and share prices. In fact, scientific citations on particular topics also follow this path. Here, in a 2012 publication, we have lithium in batteries, rare earth elements in wind turbines, and in 2012 they hadn't really taken off. But certainly tantalum in mobile phones, in capacitors, had actually reached its plateau of productivity. We're all mobile phone users. I'm sure you can perhaps remember the first time you bought your first mobile phone, and we will see that that sort of equates to when the price and demand was somewhere around here. So tantalum, obtained typically from tantalite-bearing rare metal pegmatites, also known as lithium, cesium, tantalum pegmatites, although there's some production from pyroclores in carbonatites. I apologize for the technical geology speak, but you are going to get more of it. Co-production from tin deposits until the tin crisis of the early 1980s. Principal use in electronic capacitors, cell phones, hard drives, hearing aids, and pacemakers. Unfortunately, the production and price is not transparent. It's usually based on contracts between individual producers and processors, and published statistics are usually combined with niobium. Until the mid-2000s, production was dominated by a mine in Canada called Tanco and two mines in Australia, Wodgina and Greenbushes. And in fact, since about 1960s, there have been three hype cycles. This is the real takeoff in 1978 of the electronics industry and computing with capacitors. And we can see in red the tantalum price, in black the tantalum global production. So at this point, price accelerates, global production accelerates until everyone realizes, well, we don't quite actually need quite as much as we envisaged. It goes back down, stockpiles get depleted, and then here, this is when cell phones are invented and become in general use, 1998 to 2000, price goes up again, supply goes up again, then 2006 to 2015, we have major volatility in the markets due to the closure of a couple of mines, but it's worth noting that essentially the production has increased steadily from the 1960s. We have not run out of tantalum. And according to Roskill, rapidly growing demand for tantalum was based on the wholly unfounded belief that a tantalum shortage was imminent. Demand decreased, no shortage, classic hype cycle. I'll skip that bit. Rare earth elements, a similar story, but much more recent. They are not rare, they are just difficult to extract. 1960s to 1985, most production was from Mountain Pass in California. 1984, China starts producing, and from 1988, more than 80% of the world's rare earth elements were produced in China. In 2002, Mountain Pass closed, and in 2010, we had the Senkaku incident in the Sea of Japan. This was when a Chinese fishing trawler was detained by Japanese coast guards, and there was a discussion about whose waters were the Chinese actually fishing in. This was never resolved, but the Chinese captain of the trawler was detained by the Japanese, and there were rumors that essentially said the Chinese were no longer going to supply Japan with rare earth elements. The Japanese motor industry panicked. From 2012 by 2012, there were 200 junior exploration companies looking for rare earth element deposits. That one geopolitical incident stimulated vast amounts of expenditure in the geological and mining community. If we look at something that was done in 2010 by the BRGM, the French Geological Survey, they essentially said major crises in supply and demand are predictable. That's where they had lithium and rare earths at the time, and tantalum over in the Plateau of Productivity. Southern Africa, carbonatites and rare earth element deposits. These were ones, some of which were known, but virtually none of them had a resource or reserve. We had not got a quantity of rare earth elements in these deposits in 2010. And these was the status, including Madagascar, by 2016. And all of that was added to the resource inventories between 2010 and 2016. The resources outside of China doubled. It's worthwhile mentioning that none of those rare earth element deposits in southern Africa have become mines, because the costs are too high at the moment, and China is still satisfying production. Commodity prices, stock exchange prices show sympathetic trends, such as these are some of the companies who are undertaking exploration, and you can see at the height of the rare earth element price boom, their stock prices were very good, but since then they've fallen off. From a commercial perspective, timing is absolutely everything, but if you miss the first hype cycle, you might catch the next one. The same thing has happened to lithium. It's obtained from brines in the lithium triangle, that's in South America, or pegmatites, which occur more uniformly on the planet. Used in electronic vehicles for lithium-ion batteries, and essentially recent legislation and concerns of climate change have influenced everyone, I think, in the fact that we would rather have electronic vehicles than internal combustion engines wandering around our streets. These are pictures of two lithium mines in Namibia, Rubicon and Helicon, that essentially haven't been mined since about the early 1990s, but now people are looking at reopening them. This is Bakita in Zimbabwe, which is a lithium mine. It's been a tantalum mine, it's also been a cesium mine, and in fact, it's a private company, so we don't know actually how much is there because they don't have to publish their resources and reserves, so it's actually not taken into account in the sort of accounting for worldwide lithium, if you like. And here we can see a sort of typical increase in, again, global production in black, lithium price in red, and the green is Web of Science citations for lithium deposit over the same period. So you can see that as we have an issue, scientists do more work on these things. Lithium price is soaring. It's from the Edelstein Institute. Lithium carbonate, battery grade prices. Exploration expenditure figures are difficult to quantify, but there was certainly a hard rock lithium boom or exploration boom in 2017 to 2018. These are projects in Africa, principally Zimbabwe, also the DRC and Mali, and the newly determined hard rock resources in Africa equate to approximately 3 million tons of lithium, when world production on a yearly basis is in the region of 80,000 tons of lithium per annum. So in 2 years, we've essentially found 3 million tons of lithium, which we weren't really aware of, if you like. The same trends are seen in the share prices of the particular companies, and one major effect of the hype cycle is a stimulus to exploration and an increase in the resource base, which I think is actually a good thing. It's perhaps not good from the volatility of markets, from the volatility of understanding what's actually happening. But it's also worth looking at the fact that 2016 British Geological Survey lithium profile, there's Africa, not very many spots in it. This one here, one spot in Africa, no spot in Zimbabwe for Bakita, which incidentally is the world's 3rd largest producer of lithium. And in this one here, no African deposits at all. Resources and reserves are problematic statistics. We should not use them to actually calculate how much of a particular commodity is left in the ground or is actually available to be extracted. They're not sufficient for forecasting. What we could use is something for a resource base, called a resource base, which is based on upper crustal abundance in ppm. And here's a diagram. Unfortunately, it takes the globe as a whole. So you can't really use it to sort of say, okay, how much lithium is there in South Africa? It would require much more detailed work and quite a lot of time. Also, from a mining company perspective, it wouldn't be stock exchange compliant, and they wouldn't like to rely on it. To generate resources and reserves information requires exploration and money. If it hasn't been drilled, sampled, and analysed and understood by geologists, mining engineers, and metallurgists, the statistics don't really know about it. You can't go and get a quantity. And I shall show you, I think, 2 more examples of mineral deposits that have been newly discovered and make an incredible difference to the statistics. This diagram essentially shows you what mineral resources are in various levels, purely based on geology. And that's derived typically from drilling. You have to spend money, otherwise you don't have a mineral resource. And you certainly have to spend more money to convert a resource to a reserve, which essentially is something that is mineable from terms of sort of economics, exchange rates, logistics, legal factors, environmental factors, etc. If it's a resource, it's in the ground and it might be able to be extracted. If it's a reserve, it probably will be able to be extracted. So critical raw materials vary with time and place. Perceived shortages are typically a reaction by the uninformed. However, what I've given you so far in terms of critical raw materials has been a very European, American, or Japanese perspective. They are the people producing the lists. Sure, Africa, South Africa could tap into that in terms of producing raw materials to be beneficiated either in Africa, but more typically outside of Africa. But what are the raw materials critical to South Africa and Africa? Surely those are the things we also need to concentrate on. We all know about the issues regarding beneficiation and exporting raw materials. It is obviously much better to beneficiate in country. One of the problems is, though, that all these critical raw materials, we don't need very much of them in the world at the moment. The amount of lithium we need for lithium-ion batteries is not a lot. So actually having processing plants scattered around the globe does not make economic sense, and it doesn't make environmental sense. It's much better to have a particular processing plant in one place where the environmental impacts can be constrained. Unfortunately, that means that unless you have a sort of developed ability or a developed facility for critical raw materials, it's difficult to initiate the processing of them. Water, phosphates for agriculture, cement, iron and steel, glass, sand. If we want to improve the infrastructure in South Africa, or indeed Africa, these are probably the more critical materials in the short term. This is a map of Africa, color-coded deposit types, something I actually drew up in 2010, so it is a little bit out of date. There are an incredible variety of critical raw materials in Africa and a lot of potential deposits. There isn't a shortage. We don't have to go overseas. We can have production exploitation that is sensible, that is conscious of the environment within Africa. This is an example of a copper deposit. I've put this in because if you're going to manufacture an electric vehicle, you need 4 times the amount of copper that you need in a vehicle powered by an internal combustion engine. Green energy requires more mining, not less. And this is a deposit in the western side of the DRC, recent discoveries, and it was disregarded by many due to unfavourable stratigraphy. The rocks weren't the right rocks to find this deposit. It is now the world's largest undeveloped high-grade copper deposit with a total indicated mineral resource of 1,387 million tonnes at a grade of 2.64% copper. A typical copper deposit in South America around the Pacific Ring of Fire is about 1%. This is just a little bit more geology, and this is a map showing that was the discovery, and they have extended it further to the southwest. It's not easy to make predictions. I particularly love this one. I think there is a world market for maybe 5 computers. Oh, look, there's more than 5 in this room at the moment. And that was made by the president of IBM, someone who really should have known better. And now, virtually the whole periodic table is used in the manufacture of computers. And there's almost, I'm sure we all own a computer, or we have a computer that we use at work. All of us in this room. They're not going to go away. And especially with the fourth industrial revolution, we are actually going to have more computers. To talk about electronic vehicles versus the fuel cell, which is really lithium, cobalt, and graphite in the EVs, in the lithium-ion battery, versus PGEs as a catalyst in the fuel cell. This is to some extent disregarding technological developments. It's the situation as it is at the moment. We may not need lithium, cobalt, graphite batteries in the future. Battery technology will move on. We may be using vanadium, which would be good for South Africa because we have the world's largest vanadium resources. At the moment, we have the world's largest PGE resources. But PGEs are typically, the major use is in catalytic converters in internal combustion engines. At the moment, fuel cells, which also use PGEs, there's only 3 in production worldwide. In terms of electronic vehicles, there are 23 in production worldwide. This is possibly about a year out of date. I did do this last year. Those in red are in production in China. Consequences for South Africa: more platinum is used in catalytic converters for diesel vehicles than palladium. Diesel is being banned in cities in Europe, left, right, and centre. You will not be able to go to Oxford next year and drive a diesel vehicle. In 2040, no internal combustion engines will be manufactured in the EU. We can see in blue the platinum price, in grey the palladium price. That obviously has implications for the PGE mining industry in the Bushveld. Next few slides are just a couple of not quirky but interesting aspects. This is the Orkney Islands off the northeast coast of Scotland. And the headline on the 28th of March this year was how hydrogen is transforming these tiny Scottish islands. They have abundant wind power. It is very windy up there. They have quite a lot of water. In fact, this is from tidal energy. That's a tidal energy generator. And they generate surplus energy. It's got a low population, and it generates more energy than they can use. So the surplus energy they use to manufacture hydrogen by splitting water, and they can then store the hydrogen as a compressed gas and use it in the municipal fleet in the Orkneys, which, okay, it's less than 10 vehicles, but they are all powered by fuel cells and by hydrogen. So the PGE demise, or the demise of the PGE extracting industry, may not happen. Batteries of the future. This is the sort of hype cycle with respect to lithium ion, plateau of productivity, lithium air, lithium sulfur, etc. As chemists, people will tell me about this. I'm not trying to sort of tell you anything, but I'm also aware that vanadium batteries are a possibility. So which of these is more important? The fourth industrial revolution or a carbon-free or low-carbon economy? I personally think they go hand in hand, and I'm sure you would agree as well. How we actually do it and what raw materials we're going to need is going to depend on changing technology, which will change incredibly rapidly over the next 5 to 10 years. Renewable energy will require more raw materials, not less, at least in the short and medium term. So this is concrete requirements, these are steel requirements, these are aluminium requirements, copper requirements. In essence, traditional energy generation processes are on the left, renewable energy processes are on the right. So to actually use renewable energy, we need more concrete, and to produce a ton of cement puts a ton of CO2 into the atmosphere. We need more steel, we need more aluminium, which uses an immense amount of electricity, and we need more copper. Getting the balance between all of these are difficult. I personally feel that these are misconceptions. I don't think there's a shortage. I don't think the fourth industrial revolution will reduce mining activity, and I don't think there are shortages of minerals required to provide elements for a 21st century civilized life. In conclusion, autonomous vehicles, something that's considered to be something of the future. The mining industry is ahead of the curve. Rio Tinto this year in July, this was its first journey, but now has a sort of scheduled autonomous train in Australia taking iron ore from the mine to the port. It's controlled by an operations centre 1,500 kilometres away. It's the world's first fully autonomous long-distance heavy haul rail network. Is South Africa ready for autonomous railway? Is Transnet going to be ready for autonomous railways? Education, education, education is the key. We need to have a society that is happy with autonomous vehicles. We need to have people who are educated and can help us build, maintain, run these sorts of systems. Last slide. Excellent. Disruptive technology, the fourth industrial revolution, are they buzzwords or reality? I am not going to make that prediction. I think there's an element of both in that. BMW and Daimler, two giants in the automobile sector, are pooling their resources because their vision of the future in a European city is no one owning their vehicles. You have autonomous taxis, Ubers, call them what you like, that you dial on some version of cell phone or on your watch, which is a new sort of interactive watch with GPS. That's not new, they're out already. And it will come and pick you up, take you to where you want to go, and there will be an app that will show you which route you're going to take to avoid the traffic jams. I think we would all love that, especially if we've had to come from Pretoria or Johannesburg today. I suppose, is it a coincidence that the potential lack of rare earth elements caused tremors in the car industry in 2010? Perhaps they want to be ahead of the curve again in the future. So how many of you will own a vehicle in 50 years' time? Because that obviously has implications on what we do now in terms of infrastructure development, in terms of our whole way of life. And that I see as perhaps one of the most important aspects of the fourth industrial revolution. Thank you very much indeed.